Hello and welcome to a short summary of our benchmark for deep learning reconstruction methods for low-dose computed tomography. My name is Maximilian Schmidt and I'm a PhD student at the Center for Industrial Mathematics at the University of Bremen in northern Germany. I want to start this presentation with a short motivation. So in the last years, learned methods have really boosted the reconstruction quality in many image applications, but on the same side, in medical imaging, we often only have a limited amount of paired data available or no ground truth data at all. That's why we focus on the following 3 points in our study. The first is that we compare different classical and deep learning approaches for CT reconstruction in different low-dose scenarios. Second, we investigate how the number of training and validation samples influences the power of the model. And third, we explore ways how we can use the deep image prior, a method that works without training and ground truth data for CT reconstructions. As many of you may know, CT is one of the most valuable tools in modern medical imaging, and it proves its worth in the current crisis in the detection of pneumonia. But on the other hand, there are also studies that indicate that up to 1.5% of all cancers in the US might relate to the usage of CT. So a focus point is to reduce the dose, but this can lead to challenges for the reconstruction. And in our study, we include 2 common strategies to reduce the dose. One is the sparse angle one, and here we have to deal with undersampling. We touch this in our synthetic ellipsis dataset. And the second is the low photon count. Here Poisson noise occurs, and we cover this in our low-dopap CT dataset. You can access both datasets directly through our Python library Baguer. We'll now take a closer look at the datasets. The first consists of random ellipse phantoms and has around 40,000 images in total. Here we simulate the sparse angle setup with 30 measurement angles, and the challenges are that the measurements are undersampled and we added additional Gaussian noise here. The low-dopap CT dataset uses thoracic CT scans from the LIDC database. The ground truth images are taken at normal dose. We include over 800 patients and 40,000 scan slices and simulate a low photon count setting. In this dataset, the reconstruction models have to deal with Poisson noise in the sinogram space. I now want to introduce you to the deep image prior. So the idea here is pretty simple. You take a fixed input Z in a neural network which has parameters theta, and then you want to solve the following optimization problem. Here A plays the role of the forward operator, which is in our case the 2D radon transform, and Y delta are the noisy measurements, and the network phi takes the position of the reconstruction X in this case. At the end, you will get a parameterization theta hat, which you then use to create the reconstruction X hat with the help of the fixed input Z. The nice thing here is that you don't need any ground truth data or previous training. This is basically dictionary learning. You can optimize the above problem using gradient descent or even methods of higher order, but the important step is to use early stopping. This acts as a kind of regularization, and another kind of regularization comes from the architecture itself, which are often convolutional neural networks. So we can build upon the idea of the deep image prior and improve it even further. And the first idea is to combine it with classical regularization. So we add an additional term with a weighting factor alpha, and in our case we decided to use the total variation, which will result in sparse gradients and is often used for CT images. The second approach is to choose Z not randomly, but take it from the output of another reconstruction algorithm, for example learn Primal-Dual. And since we are taking a good initial guess with our Z, this can lead to better reconstruction and fewer optimization steps. As an additional bonus, the deep image prior can be used to adapt the initial algorithm to a new setting without having to retrain it. So if you change the CT machine or the noise setting, it's often not feasible to really retrain the basic model, but in this case the deep image prior acts like a translator from the old to the new setting. Now we come to the heart of our study, which is the comparison of different methods on the 2 datasets. And here we include 4 different kinds of models. The first work without any training data. The second tries to fully learn the inversion process. The third are learned iterative schemes, which use unrolling to display the process as a neural network. And the fourth are post-processing algorithms. We'll start with the ellipsis dataset, and here you can see the values of PSNR and SSIM on the test set for increasing sizes of the training set. Here 0.1% means as little as 32 data points. You can see that our approach of the Learn Primal-Dual in combination with the Deep Image Prior works really well in the low data regime. And if you don't have any training data at all, it seems like a good alternative to use our Deep Image Prior in combination with TV. On the loaded-up dataset, we start with as little as 3 images coming from only one patient. And the results are similar to the ellipsis, but there are 2 exceptions. One is that our approach of the Deep Image Prior with the TV works even better than before, and only Learn Primal-Dual and FVP plus the UNet are able to surpass it here. The second is that the combination of Learn Primal-Dual and the DIP didn't result in any improvements, and that's why we don't include it here in the study. So as a summary, if you don't have any training data or only a little amount, it might be worth to combine your methods with our Deep Image Prior approaches. And in general, it's a good idea to include as much knowledge about the problem as possible in your model itself, like you do in the Learn Primal-Dual. This concludes my short presentation of our benchmark. My colleagues and I want to thank you for your attention, and if you want to have more information, just scan the QR code or follow the link below. There you will find our preprints, example reconstructions, and the link to our GitLab page. We wish you a nice conference, stay healthy and safe, goodbye.